Hi everyone, and welcome back to the MCAT A series of lectures in physics. In the previous lecture, I discussed one of the two types of energy transfer process that can occur between two systems or a system and its environment. In this lecture, I shall discuss the second type of energy transfer process known as heat. In particular, I shall focus this discussion on energy transfer in terms of gases. Gases are simplest to consider as the atoms and molecules within a gas can move freely. We do not have to concern ourselves with the forces that are in play between the atoms and the molecules. Temperature and heat are often confused in the real world. In this lecture and the following lecture, I shall discuss the differences between the two. Similarly, I shall also discuss what is meant by the pressure of a gas and how that gas pressure relates to its temperature. Thermal expansion will then be discussed, which revolves around what happens to the size of an object as it is heated or cooled. Then I shall break up typical systems into three different categories, defining what the differences are between all three. Some of the laws of thermodynamics that you need to know for the MCAT will then be discussed in detail, before I finish this lecture discussing various different ways in which heat is transferred. This video is the first of two parts on heat, being a more general introduction. The second part will then use these concepts and focus in more on gases. To begin, temperature is something I'm sure you've come across before and has to do with how hot or cold an object is. More precisely, at the atomic level, temperature is related to the kinetic energy of the particles. For example, to simplify things, let's just look at a gas. In a gas, the atoms and molecules are not tied to each other and therefore move about at random speeds. The temperature of that gas is then related to the average kinetic energy of these particles. In other words, although each atom and molecule has its own associated kinetic energy, overall, all of the particles have an average kinetic energy. Kinetic energy, as I discussed in a previous video, is equal to 1/2 mv squared. Therefore, kinetic energy is related to the velocity. In other words, temperature is in some way related to the velocity of the particles. Although the velocity of each particle is in some way randomized, overall, the gas will have an average velocity and therefore an average kinetic energy. To quantify the size of the temperature, in America we typically use units of degrees Fahrenheit, degree capital F. You may also be familiar with degrees Celsius, what is commonly used in the real world in Europe and elsewhere. Both the Fahrenheit and Celsius scales are based on the phase changes of water. For example, the freezing point of water is defined as 32 degrees Fahrenheit or 0 degrees Celsius. Similarly, the boiling point of water is defined as 212 degrees Fahrenheit or 100 degrees Celsius. In the MCAT and in scientific study in general, we typically instead use what is known as the Kelvin scale, capital K. In the Kelvin scale, we instead define 0 degrees Kelvin as the temperature at absolute zero. Absolute zero is the theoretical temperature at which there is no movement of particles. All the particles are not in motion. This value is a purely theoretical concept. Even in solids, for example, the particles vibrate. There is some motion and therefore there is some temperature. However, this is a useful unit to use as we never get a negative sign. 0 is always the smallest possible temperature. As I discussed in my first video, this is one of the 7 base units. Kelvin is a base unit. Something you need to know for the MCAT is how to convert a temperature value that is in one unit into another unit. For example, if a question gives you a Celsius unit and tells you to find it in Fahrenheit, this is the formula you would use. The value in Fahrenheit is equal to 9/5 of the value in Celsius plus 32. A similar formula can also be found to calculate the Celsius value if given the Fahrenheit value. All you need to do is rearrange this equation for capital C, and I will leave that with you for you to practice with. The relationship between Kelvin and Celsius, however, is much more straightforward. Kelvin, if you like, is simply a shift of a Celsius value. For whatever the value is in Celsius, the Kelvin value is roughly 270 degrees larger than that. The reason I say roughly is because it is actually equal to 273.15 and so on and so forth. As the Celsius scale is related to the phase change of water, and as the Kelvin scale is instead related to absolute zero, you do not have that exact number difference. The phase change of order and absolute zero are not related in such a clean fashion. However, for the MCAT, you may assume that the difference between them is 273 unless otherwise stated. As I have stated, temperature is related to the average kinetic energy of the particles. Heat, however, as I discussed in the previous video, has to do with energy transfer. Therefore, heat and temperature cannot be the same thing. Instead, heat is associated with a temperature change. Anytime there's a temperature change in a system, heat is lost or gained from that system. For example, let us consider the simple case of a gas inside of a box. As a gas, each of the atoms or molecules within the gas are moving randomly at certain speeds. Temperature, remember, is related to the average speed of those particles. Therefore, if heat is lost from the system, the average speed of those particles must decrease. This could be done, for example, because the box is not perfectly insulated. Insulation is something I shall discuss further later, but it has to do with heat being lost from the system. As with the other energy transfer process work, heat naturally has units of energy. The units of energy are therefore joules capital J. If, on the other hand, that gas gained heat, then the particles within the gas on average would get faster. This could be done, for example, if the box was heated up, either by being placed in a hotter environment or by being placed over a flame. We can also consider the pressure of a gas in a container. Pressure is defined as the force exerted by a substance per unit area. In other words, how spread out that force is. The pressure of a gas in a container is therefore the force that that gas exerts on the walls of its container. Naturally, if we increase the number of particles in the gas, then the pressure of that gas will increase. If there are more particles, then the force on the walls of the container will naturally be bigger. Each particle will exert a force every time it hits a wall of the container, and therefore if there are more of them, the overall force is going to increase. Likewise, if the temperature of the gas is bigger, then the pressure will also be bigger. If the gas temperature is bigger, then the average velocity of each particle will also be bigger. Remember, temperature is related to average kinetic energy and therefore average velocity. If the average velocity of each particle is bigger, then naturally the force exerted by the particles on the walls of the container will also be bigger. Finally, the pressure of a gas also increases when the size of the container it is within decreases. In other words, when the volume of the gas decreases. This is because if the container size decreases, then the number of gas particles that hit the wall in a certain instant of time increases. Therefore, the force exerted by the gas on the walls also increases, thereby also increasing the pressure. This relationship between gas pressure, gas volume, gas temperature, and the number of particles within the gas will be explored in the next video when we talk about what is known as an ideal gas. We shall also look again at pressure when we come to liquids, and it is then when I shall also talk about the units involved with pressure. As I mentioned, temperature has to do with the average kinetic energy of the particles. Therefore, on average, the energy of the particles within a particular object will be bigger. As these particles are bouncing around more, if you like, this results in the size of that object changing. It causes the size of the object to increase. To demonstrate this, let's first look at a simple case of expansion in only one dimension. Let us consider that at temperature T0 we have a rod of length L0 as shown. If we then increase that temperature, as I mentioned, the length of that rod is going to increase. The change in length of that rod can be calculated as follows. The amount by which the rod length increases is dependent upon three different factors. The first factor is the original length of the rod. Naturally, the fraction of change of the length of the rod is dependent upon how big the rod originally is. Also, of course, the amount by which the rod expands is dependent upon how big the temperature change is. For example, if the temperature increases from 20 to 25 degrees Celsius, we would expect the rod length to not expand as much as, say, a 20 degrees to a 1000 degrees Celsius change. Naturally, if the temperature is 1000 degrees, then the particles are moving on average much quicker than, say, at 25 degrees Celsius. The temperature difference is important in determining the overall amount of expansion. Finally, the material of which the rod is made of is also an important factor. Some materials expand more than other materials. Given the same rod length and change in temperature, rods made of certain materials will expand more than other rods. Therefore, the material of which the rod is composed of must factor in some way. Overall, the change in length of the rod delta L is given as follows. That change in length is equal to alpha, which is known as the coefficient of linear expansion, multiplied by the original length L sub 0 multiplied by the change in temperature. The coefficient of linear expansion alpha is the factor that is associated with the material of the rod. Alpha is different dependent upon what the rod is composed of. Of course, more generally, it is not simply the length of an object that expands, but more its volume. Its volume can increase or decrease dependent upon the change in temperature. In other words, in general, there is a different formula for the change in volume. The change in volume is given by beta V sub 0 delta T, where again V sub 0 is the initial volume at temperature T sub 0, and delta T is the change in temperature. Beta, just like alpha, is known as the coefficient of volume or volumetric expansion. Although this relationship is not exactly true, you may assume it is true for the MCAT. The coefficient of volumetric expansion is simply equal to 3 times the coefficient of linear expansion. In other words, beta is equal to 3 alpha. Let us now consider an example to demonstrate this. Let us consider a glass rod. This glass rod has a coefficient of linear expansion of 2 multiplied by 10 to the minus 6 inverse Kelvin. Hopefully this unit makes sense to you. If you solve the previous equation for alpha, you will see that it has units of inverse temperature. Let us assume that this rod has an original length of 2 meters at 300 degrees Celsius. Then, let's say that this rod is cooled to a temperature of 100 degrees Celsius. For example, this could be a glass rod that was just made by a blacksmith and he has just taken it out of a fire. The question could then ask us what is the change in length, or, as in this case, it could ask us what is the final length. In other words, what is the initial length plus the change in length. In this example, as the rod is cooled, we would expect the length of the rod to decrease. This will be reflected in our answer by getting a negative change in length, as we shall see shortly. Remember, the change in length is equal to alpha L sub 0 delta T. Alpha, we are told, is 2 multiplied by 10 to the minus 6. L sub 0 is equal to 2 meters, and delta T is the final temperature minus the initial temperature, 100 minus 300. Hopefully some of you have noticed a mistake that I made here. The coefficient of linear expansion is in per Kelvin. However, the temperature is not in Kelvin, it is instead in Celsius. Luckily, this is not an issue in this case. Remember, the relationship between Kelvin and Celsius is simply the addition or subtraction of 273. Therefore, as I am working out a temperature change in Kelvin is the same as a temperature change in Celsius. In other words, instead of having 100 minus 300 here, I should have 100 plus 273 minus 300 plus 273. Those 273s would cancel. I'd get 273 minus 273. Hence what I have is correct, and therefore working that out, we get that the change in length is equal to minus 0.0008 meters. Therefore, the final length is equal to the original length plus this change in length. The final length is equal to 2 meters plus minus 0.008 meters. In other words, working this out, the final length of this glass rod is 1.992 meters. The fact that this length change is small makes sense. We know from real-world examples that putting a glass rod into a flame, you do not see visually with your eyes the length of that glass rod changing noticeably. Such length changes are typically subtle unless the change in temperature is very, very large. Therefore, ensure for the MCAT that you feel comfortable dealing with such small numbers using scientific notation. Before moving on, I would like to classify what is meant by a system. A system is an object or a collection of objects that we are interested in observing, experimenting on, or manipulating. Anything that is not the system we call the surroundings. As I mentioned previously, we can talk of heat being exchanged between the system and its surroundings. However, as we shall see shortly, particularly in the next video, it is a good idea to split systems into 3 different categories. The first type of system is known as an isolated system. For an isolated system, both energy and mass cannot be exchanged between the system and its surroundings. Naturally, in the real world, such systems are very rare if they exist at all. Perhaps the only thing that can be considered a true isolated system is the universe itself, although some scientists would even question that statement. A more realistic system is that of a closed system. In a closed system, energy is allowed to be transferred between the system and its surroundings. Mass, on the other hand, is not allowed to be exchanged. For example, as we shall see shortly, we can have a gas inside of a container and a piston compressing that gas. Finally, and as you may have guessed, is an open system. In an open system, both mass and energy can be exchanged between the system and its surroundings. For example, we can consider water in a kettle. If we consider both the water and the kettle as the system, then not only is energy being lost, but also mass. Some of that water is turning into steam, which leaves the system. As that steam has mass associated with it, both energy and mass are leaving the system. As I mentioned, classifying systems in such a way will become more important for the next video. Now I would like to turn my attention to the laws of thermodynamics. Before discussing the first law in detail, I would like to mention what is known as the zeroth law. You can consider this law being known as the zeroth law rather than the first law because it seems trivially obvious. The zeroth law states the following. Let us say we have an object A and an object B that are in thermal equilibrium. Thermal equilibrium means they both are at the same temperature. There is no heat exchange between object A and object B. Let us further assume that object B and object C are also in thermal equilibrium. If object A and object B are in thermal equilibrium, and object B and object C are in thermal equilibrium, all the zeroth law tells us is that object A and object C are also in thermal equilibrium. This is of course a simple observation, so therefore I shall not discuss it in more detail. The first law of thermodynamics, if you like, is simply the law of conservation of energy for thermodynamics. As I mentioned previously, energy can only be transferred between a system and its surroundings if either one of two things happens. Either work is done on or by a system, or heat is lost or gained by that system. To be more precise, we say that the change in internal energy capital U of a system can only occur because of those two things. We use the term internal energy to distinguish the fact that the system itself may also be moving. For example, we could have a box that contains a gas, and the box itself could also be moving. Therefore, that box would also have an associated kinetic energy. To distinguish what is happening with the box itself, we instead talk about the gas's internal energy, the energy associated with the atoms and molecules within the gas. Again, as I mentioned, such internal energy can change because of one of two things. To show this, let us consider a cylinder that contains a gas of internal energy U. Let us also assume that this gas is being kept here by a piston above the gas. The internal energy of this gas, as I mentioned, can change because of one of two things. Firstly, heat can be exchanged between that system and its surroundings. For example, we can consider holding this container above a flame. If it is held above a flame, then heat flows from that flame into the container. There is a net heat exchange between the system and its surroundings. This will result in an increase in the internal energy of the system. Likewise, we can consider heat being lost from the system. For example, looking at a hot cup of coffee, over time, that coffee is going to lose heat. It's going to get colder. This is done because there is heat exchange between the cup of coffee and its surroundings. Heat flows from the cup of coffee to the surroundings. Also, we can consider a change in internal energy due to the second energy transfer process, known as work. Again, going back to our example of a container of gas, we can consider moving this piston up and down. For example, if we move the piston down, we say that work is being done on the gas. Moving that piston down decreases the volume of the gas. As I mentioned previously, because the volume of the gas has now changed, the internal energy of the gas has also changed. Likewise, we can consider lifting the piston up, thereby increasing the volume of the gas, also resulting in a change in internal energy. Overall, both of these energy transfer processes can be summed up by the first law of thermodynamics. It is stated as follows. The change in internal energy capital U is equal to the sum of the energy transfer processes, which due to convention we write as Q minus W rather than Q plus W. Capital Q represents the heat gained or lost, and W represents the work done or by the system. The signs of all three quantities, delta U, Q, and W, can be positive or negative. Delta U is positive if there is an increase in temperature. Based on the definition of temperature, if there is an increase in temperature, there is an increase in the kinetic energy of the particles, and therefore an increase in the internal energy of the system. Likewise, if heat enters a system, then there has been an energy transfer from the surroundings to the system. Overall, the internal energy of the system has increased and therefore Q is positive. Q is instead negative if heat leaves the system, if heat goes out of the system. Finally, let's be careful about this minus W. Because by convention we have a minus here, we have to be careful. If work is done by a system, we would expect that system to lose energy. If the system is doing something, there must be an energy transfer from the system to the surroundings. Therefore, we would expect the internal energy of the system to decrease. Because there is already a minus in the equation, we therefore take W as positive. Taking W as positive in this case results in a minus, a positive number, and therefore a decrease in the change in energy. If work is instead done on a system, then energy is transferred to the system. If energy is transferred to the system, we would expect the change in internal energy to be positive. As we have a minus W, we must have minus of a negative value. Minus by minus equals plus. Therefore, hopefully the signs of delta U and Q in particular make sense, but just be careful about capital W. By convention, we use a minus W in our equation. If the work is being done by the system, we would expect the change in internal energy to be negative. We would expect the system to lose energy. This can only happen if W is positive and therefore we have a minus W, a minus a positive number. Please pause and make sure you understand this concept before moving on to the next portion of the video. Finally, in this video, I shall only briefly discuss the second law of thermodynamics. This is because in the next video, I shall define it more precisely. Roughly speaking, however, it can be defined as follows. Let us consider we have two objects, object A and object B, and let us assume that object A is much hotter than object B. The second law of thermodynamics states that heat will flow from object A to object B. In other words, object A will transfer energy to object B until both objects are in thermal equilibrium. In other words, it is not the case that object B would transfer energy to object A. Again, this statement will be defined more precisely in the next video when I talk about what is known as entropy. To finish this video, I would like to now focus on one of the two types of energy transfer processes known as heat. In particular, rather than looking at how heat is transferred between one object to another, I would now like to analyze how heat is transferred through the object itself. In total, there are three different ways in which heat is transferred through an object or substance. The first heat transfer process is known as conduction. Conduction involves heat transfer via vibrations. For example, let us consider a simple rod. And let's assume that we have a heat source on one side of the rod, for example, a flame. According to the second law of thermodynamics, as the flame is hotter than the rod, heat will flow from the flame to the rod. This will increase the internal energy of the rod. In other words, it will increase the kinetic energy of the particles within the rod. The rod, remember, is a solid. In a solid, the particles do not move about freely, but instead vibrate in place. Therefore, adding internal energy to a solid merely increases those vibrations. Therefore, particles near the heat source will vibrate more. Such vibrations can be transferred to nearby particles. A particle that is vibrating will hit or interact with a particle nearby, causing that to also vibrate. This will go on and on and on until the heat is transferred throughout the rod, increasing the vibrations from left to right. This is what is known as conduction. This is the primary method of heat transfer in solids. In most liquids and gases, conduction is not a very good method of transferring heat. This is because the particles are more spread out, the density is much less. Therefore, an increase in kinetic energy of certain particles cannot be easily transferred to other particles because collisions are much less frequent. Also, not all solids are as good as other solids. For example, due to their atomic structure, metals are considered good conductors of heat. This is why, for example, a lot of pots and pans are made of metal. Such metals can transfer heat easily to the food that is being cooked. Other solids are considered bad conductors or good insulators. An example of such a solid is plastic. While the pots and pans are made of good conductors, you would not want the handle of your cutlery to be made of a good conductor, otherwise your hand would get hot. Instead, such handles are made of insulators, for example, plastic. Plastic does not allow these vibrations to transfer easily. Therefore, you do not get a heat transfer from the hot food to your hand. As I mentioned, in liquids and gases, also known as fluids, conduction is not a good method of heat transfer. Instead, the primary method of transferring heat is instead done by what is known as convection. To understand convection, let us consider a bowl of water. Underneath that bowl, let's assume that we have a heat source, for example, a flame or a fire. Again, according to the second law of thermodynamics, thermal energy or heat is transferred from the flame to the liquid. This causes an increase in the average kinetic energy of the particles near the bottom of the water. As these particles now have a greater average speed, these particles now have enough energy to rise in the liquid. In other words, there is an overall movement of more energetic particles upwards and less energetic particles downwards. These less energetic particles are now closer to the heat source, and now they also increase their average kinetic energy. While the heat source is still present, this heat transfer process continues until overall the liquid is at the same temperature. Hopefully it is obvious why this is not a good heat transfer process for solids. In solids, the particles cannot move freely. Instead, as I mentioned, they can only vibrate in place. Therefore, we cannot get this bulk motion to the left or right in, for example, a rod. Note also that both conduction and convection need particles in order to transfer heat. Conduction involved highly vibrating particles interacting with low vibrating particles nearby. Convection also involved particles. Convection involved the bulk motion of highly energetic particles away from a heat source. This final form of heat transfer, however, does not require particles. It can instead take place, for example, in a vacuum. This method of heat transfer involves what are known as electromagnetic waves, something we will talk about in more detail in a future video. Simply put, however, energy is transferred or radiated from a heat source using waves. For example, putting hands over a flame causes your hands to get hot. However, if you think about it, it can't be conduction or convection that is causing that. Similarly, the sun is heating up the earth, even though there are very few particles between the sun and the earth. Again, this form of heat transfer has to do with electromagnetic waves, and I shall discuss in detail different types of electromagnetic waves in a future video. As I stated at the start of this video is the first of a two-part topic. In the next video, I shall focus more in on what is known as an ideal gas. I shall also define more exactly what is meant by the second law of thermodynamics. Before moving on to this video, however, let's make sure that we understand the basics behind thermodynamics. This first question, for example, is making sure we know the units of temperature. Which of the following is not such a unit? Is it Celsius, Joule, Kelvin, or Fahrenheit? Well, again, from your day-to-day lives, I'm sure you know that Fahrenheit is definitely a unit of temperature. Also, outside of America, Celsius is commonly used in day-to-day lives. And finally, I stress that in the MCAT and in science in general, we typically use the Kelvin for temperature. Kelvin is the metric unit for temperature. It is a base unit. Therefore, Joule, which I hope you remember is instead a unit for energy, is not a unit of temperature. Remember, temperature is not a type of energy. Heat is a type of energy transfer process, but heat is also distinguishable from temperature. Anytime there's a change in temperature, we get a transfer of heat. This next question is making sure we understand the differences between the different types of states. Remember, I defined a state as the object or objects we are interested in, the objects we are studying. I defined an open system as a system that can transfer both matter and energy to the surroundings. A closed system can only transfer energy. An isolated system, on the other hand, is, if you like, a super closed system. It does not allow energy or matter to be transferred. As no energy or matter is transferred from the system to the surroundings in an isolated system, the internal energy of that isolated system cannot change. Therefore, as the question is asking us which of the following systems has no change in internal energy, the answer must be an isolated system. Finally, let us look at a question that involves some numbers, namely a question about thermal expansion. In this question, we are told that we have a rod of length 20 centimeters and that it is at an initial temperature of 30 degrees Celsius. We are also told that the coefficient of linear expansion alpha for the rod is 2 multiplied by 10 to the minus 6 inverse Celsius. Remember what this alpha means. This alpha tells you how good the rod is at transferring heat. Different objects will have different alphas depending on what they are made of. The question then tells us that we want to increase the length of the rod by 0.01%. We are then asked, if we want to achieve this, what must the final temperature of the rod be? Well, in any question that involves numbers, it's always a good idea to write down what you know. We know that the original length L sub 0 of the rod is 20 centimeters. We also know that the rod is at this length at a temperature of 30 degrees Celsius, T sub 0. And again, the coefficient of linear expansion is 2 multiplied by 10 to the minus 6 inverse Celsius. Unlike in the previous example I showed you, we don't have to worry about Celsius and Kelvin. Temperature is in Celsius and alpha is in inverse Celsius. We have no problem there. As we are told the length is to increase by a certain amount, we then use the thermal expansion formula for length, the one-dimensional equation. This equation, to remind you, is given as follows. The change in length of a rod is equal to the coefficient of linear expansion alpha multiplied by the original length L sub 0 multiplied by the change in temperature. We are being told in the question that the percentage at which the rod length increases is 0.01%. Therefore, it would be a good idea to rearrange this equation for delta L over L0, in other words, the fractional change in the length. Therefore, we get delta L over L sub 0 is equal to alpha delta T. Well, delta L over L sub 0, as I mentioned, is simply the fractional change in length, so all we have to do is change that percentage into a fraction. 0.01% is the same as 0.01 over 100 as a fraction. That is equal to alpha, which we are told is 2 multiplied by 10 to the minus 6, multiplied by delta T. We can therefore solve this equation for delta T, and doing so gives us 50 degrees Celsius. The change in temperature is 50 degrees Celsius. The change in temperature, remember, is simply the final temperature minus the initial temperature. T sub F minus T sub 0 is therefore equal to 50. And therefore, solving this for the final temperature, we get that the final temperature is equal to the change in temperature plus the initial temperature, 50 plus 30, which is 80 degrees Celsius. Therefore, the correct answer in this case is option B. This video, as I mentioned, is more of an introduction to heat. In the next video, I shall discuss the idea of heat in more detail and also introduce the concept of what is known as an ideal gas. I shall also give many scenarios in which the first law of thermodynamics simplifies down. Therefore, before moving on to the next video, please ensure that you are comfortable using the equation associated with the first law of thermodynamics, namely that the change in internal energy is equal to the sum of heat and work done on the system. I hope this video has been helpful for you, and I shall see you guys in the second video on this topic of thermodynamics.